Right now, we are in the world of elementary particles. And here in this video, I'll be talking about resonance particles. And most of these elementary particles that we have, most of these particles are unstable and they decay to other elementary particles through various interactions. And if the particles decay through weak interactions, if I talk about weak interactions, in this case, they have the average lifetime, or we call it mean lifetime, of the order of 10 to the power of minus 13 seconds. And if we have decay through electromagnetic interaction. Now, in this case, the mean life is of the order of 10 to the power of minus 16 seconds. But talking about the interactions, I mean, if the particles decay through strong interactions, if they decay through the strong interactions, then their mean life is extremely small, and that's of the order of 10 to the power of minus 23 seconds. So this time is very, very small. Okay. And the existence of the particles decaying through this strong interaction, it cannot be observed directly. It is not observed directly. This is because they live for very small interval of time. But certainly they are inferred from the decay products only. So the final products, they are inferred in terms of the products that are obtained while the decay processes. Now, the short-lived elementary particles decaying through this strong interaction, they are called basically resonances. So now, why they are called resonances? Because these particles are of hypothetical intermediate states in the reaction, in the chain reaction. So they are basically the hypothetical intermediate states in a reaction or in a decay process. And moving on, the lifetime of resonance particles is very small. This lifetime is of the order of 10 to the power of minus 23 seconds. And these particles, if we talk about the distance they can travel for this period of time, if I take that distance as, say, for example, if I take that distance as d, so that will be vt. So taking the speed 3 to 10 to the power of 8 times 10 to the power of minus 23 seconds, and what it will give us is, it's going to give us 10 to the power of minus 15 meters. And this 10 to the power of minus 15 meters it's approximately the diameter of a proton. Diameter of a proton. Very small, extremely small. So before decaying, these particles stay in the dimensions of 10 to the power of minus 15 meters, which is basically the diameter, the approximate diameter of a proton. Such small distances cannot be measured by any device or any kind of chamber or bubble chamber and all that. Hence, such properties cannot be detected directly. Now, the process of such undetected particles can be determined by measuring scattering cross-section. Now, the scattering cross-section of the particles. we have two particles, let us assume particle 1 and particle 2, they collide and they have a cross section. I mean, if we take two beams of the particles having certain energy, okay, and moving towards each other, allowed to collide, the collision between the particles is caused by the cross section. The reason for the collision is the cross section. It's caused by the cross section of the particles. Now, the probability of collision between the particles is directly proportional to this cross section. It's directly proportional to this cross section of these particles. So I should say here that as a result of collision between the two beams of particles, what it does, it measures the cross section of the particle. So we can measure the cross section of the particle. If I take a typical graph, say this is the energy, say in giga electron volts, and here we have the cross section, say in nanobars. Okay. And in a typical interaction, we have a graph like this. I mean, what does this graph tell us? This graph tells us that the cross section of the colliding particles changes with the total energy in the collision. I mean, each peak, if I take this as a peak, okay, if I take this as a peak, now each peak of the graph is interpreted as the presence of these resonance particles. Resonance particles. And the energy corresponding to this peak that we have, the energy that we have corresponding to this peak is the energy of the resonance particle corresponding to that peak. Now, if I assume that we have delta t, if I take the lifetime, if I take the lifetime equal to delta t, and this is the lifetime of resonance, the lifetime of the resonance particles that we are talking about here, and this lifetime can be determined by uncertainty principle. What we have is del E, del T is equal to h cross by 2. So what will be delta T here? This is going to be h cross by 2 delta E. Now, what is this delta E? This delta E can be measured from this graph. It is the width of the peak at the half maxima. It's the width of the peak at the half maxima of this graph. So by virtue of Heisenberg's uncertainty principle, what we can is we can calculate this lifetime of these resonance particles, okay.